All right, guys. So we have chapter 4, which is Introduction to Newton's Laws of Motion. All right. So we're going to be basically talking about what a force is, what the definition of force is, how we can represent a force as a vector, and how we can do vector addition of forces. So basically, force is a vector. That means everything that we learned up to this point, how to do, let's say, vector addition, vector subtraction, right? You know, working with vectors, drawing them tip to tail, parallelogram method, all of those things we can now apply to forces. Then we have Isaac Newton, who basically gave us 3 laws of motion, and we're going to be going over those in this chapter. So this is very introductory chapter, and then the next 2 chapters, chapters 5 and 6, will then be much more, let's say, application, oriented. So here we are talking about the laws of motion. What are the first law, second law, and a third law? And then, very basic, let's say, examples. And then we're going to go and look at much more, let's say, um, complex applications in next few chapters. But it's important, that kind of like not to take this chapter lightly, right? Because we're going to be talking about all the fundamentals of the, let's say, Newtonian, what we call dynamics, and how to, work with the forces. What is a force? Who applies force? What force does to the object, and all of those things we will be then covering in this chapter. All right, so you can say that, you can see over here, right? So the physics can be separated into 2 distinct parts: statics and dynamics. Okay, so generally statics means, when object is not moving, or uh, in a way you can say that it's not moving, but let's say, because not moving is one of the examples of statics, but statics is something that we already worked with. We called it uniform. So uniform, which means the object here is in uniform motion, not a uniform circular motion, but uniform motion, which means object is not accelerating. Basically, there is no acceleration, and acceleration velocity itself is 0, and velocity is constant. Then remember, acceleration 0, velocity 0 means object is not moving, but acceleration 0, velocity not 0 means object is moving with constant velocity, not speeding up, not slowing down, not changing direction, basically moving in a straight line. Then we have dynamics, and dynamics, we also have covered that, and this is nothing but a non-uniform. So non-uniform motion. All right, so we covered this as well. And what was the difference between uniform and non-uniform? Well, exactly this, right? The acceleration. So we said that whenever there is an acceleration, object is in a non-uniform motion. So, and we could describe how the object is moving. Well, the difference here is this. When you talk about dynamics, then it kind of adds an extra layer to that. That means we're not going to be able to understand now not only how the object is moving, but why the object moving the way it does if it's in a non-uniform, motion. That means, why is the object speeding up or slowing down? Why is the object changing direction? What makes the object basically, change velocity technically? Because remember, acceleration is, in any, in one way or another, is changing velocity, either by changing speed or changing the direction. And the dynamics explain not only how, but like, let's say, why the object is doing the way, let's say, doing what it is, in terms of understanding this concept of forces. All right. So that means, in a way, we're going to see that acceleration, right, is related to this concept of forces, because in chapter 2, 3, we talked about, let's say, all right, so there's a change in velocity. Oh, that's because there's acceleration. But we never really said, why is there an acceleration? Where does that acceleration coming from? Who gives the car, let's say, an acceleration or thing like that? Well, this is a chapter for that. In this chapter, we're gonna be learning about all of that. We're gonna be able to understand why the acceleration of the object let's say in the direction of the velocity, and it's making it speed up, and y, the acceleration when it's in opposite direction, make it slow down, and all of those things. All right, so in any case, let's say to put everything into like one, let's say sentence, acceleration is due to a force. All right, now the question here is, what is a force? How do we define force? How do we draw force? What type of forces can we have on the object? So those are the things, we're going to be then looking at in this chapter. So that's why it's an introductory chapter on what is a force? How do we work with the force? How do we draw the force? How do we calculate forces and all of those things? And we start by probably the simplest explanation of a force, which probably all of you more or less can already figure out. Force is some kind of push or pull. You push something, you pull something, right? That's basically force. So think like this. So you have a box, and this box initially at rest. So V initial equals 0. So in order to make this box go from this X initial to this X final and have it some kind of non-zero final velocity, what do? How do we make this object move? Well, previously we would say, oh, we give it an acceleration, which will then change the velocity. Yeah, that's good. But let's say now the question is, why it will change the velocity? Based on what? Let's say, where does this acceleration coming from? What do we do to make this acceleration an object to change its velocity? Now we can say, well, you push the box. You push the box, and box is going to then start moving, from rest, it's going to start speeding up. Okay, or you can pull, right? Depending, like, let's say maybe there's someone over here pushing, or maybe someone over here pulling by a rope or something like that, right? But in any case, there is a box that, in order for it to speed up or slow down or change direction, right? All of those things, well, we need a force, okay? And the simplest way you can think of it, it's some kind of push or pull, right? Something pushing or pulling. So then that's, let's say, you can think of, like, let's say the best example of how you define force. All right, so a force, some kind of push or a pull. Now, force, generally what happens here is this. It's an interaction between two objects. Let's say here you have two objects, right? You have a box and you have a person who pushing the box, and they're interacting. So then one of the way we, kind of like, let's say, separate those two, we want to, let's say, define one that is doing the pushing as an agent. So I'm going to say this is the agent. So agent is whoever pushes or pulls. And the object that is being pulled or pushed is then going to be the, object. So this is our object, all right? That means any object that is being pushed or pulled can then be used to describe, let's say, its motion. So that means what I have here is that, agent exerts force on the object, and then I can look at what happens to the object because of that force. Again, you can see, right, here's the interaction between, two things, which is basically, again, it's another person pulling this time. So here's the agent, and here's my object. Okay, that's my object. Well, this is the same thing. Here's another, example of interaction. But the difference here is this. For the first two, you see a contact, right? You see actual contact between an agent and an object. But here we don't see it. It seems like, you have an object, you have a ball, right? You let go, it's going down. Okay, so I don't see anybody pushing or pulling directly. But there is somebody who's pushing or pulling indirectly, and that's, Earth does that. And when Earth, exerts force, it's, you can say that it's a long range force, or sometimes we call that a field force, okay? So the gravity is an example of a force that acts over a distance. So again, that's why probably the long range force or a field force is, very appropriate. You don't see any type of, pull or push, but it is moving because of the effect of that, let's say, force from Earth. There are two other forces that we're going to be working with that's similar to gravity, not in physics 6, but in physics 7. And those are electric force and magnetic force. Those forces also act over a distance. That means you don't see anyone pushing or pulling. That's why you take a magnet, bring it close to your refrigerator. As soon as it's like really close, you don't see anybody pulling, right? But it will basically be pulled and, it will stick to your, refrigerator, okay? You don't see like actually like this, let's say there's a hand pushing or something like that. When it's close enough, that magnetic pull exerts force, and then, your magnet is attracted to the refrigerator and, basically moves and gets attached. All right, that means, in a way we have contact forces and we have long range forces, right? So long range forces. And you can say that those are the two types of forces we're going to be working with. All of our forces except gravity in this physics 6, pretty much a contact force. Only gravity is a long range force. In physics 7, then we have a couple more long range forces, but here you can say that in physics 6, it's gravity only a long range force. All right, so one of the things we can have here, let's say when you have an object, well, you can have one object, but you can have many agents exerting force on the object, okay? So let's say if you can see, right, example here. So this is a box, and box there's a drawing of two vectors, one vector up, one vector to the left. Now, remember, any quantity with the arrow on top is a vector. And that's an example of basically two forces acting on the box. That means there are two agents, right? So acting on it. So technically that's an example of actually one agent, that's the surface, for example, acting on the box. But when the surface acts on the box, it usually acts at an angle like this. Okay, like here's a surface, here's an angle. And when you break it down into two components, then you have perpendicular and parallel. We're going to talk about those. In this chapter, we're going to talk about, let's say, perpendicular to the surface component of the thing like this. So this is technically surface force. That means if you have a box on a surface, that surface, remember, like let's say interaction between two things. Here, box is interacting with the surface, and then surface exerts force. But the surface technically then, you can say exert one force that is perpendicular to the surface. We call it N for a normal force. So this guy here, a normal force. So we kind of already talked about contact forces, right? Pushing or pulling. Technically, normal force is a contact force as well, but not like, let's say, push or pull. It's a, push from the surface, you can think like that. But here's a normal force, which is always perpendicular to the surface. Then there's another one where there's a parallel to the surface, okay? So this is, we call it friction. But this friction is not something we're going to be, looking in the greater detail. We're going to wait until chapter 5. Remember, most of those important, and complex application is in chapter 5. But here's, let's say, a friction, lowercase f. And those two together are component of pretty much this surface force. So this is the actual surface force and normal force and friction components. We never really use this. We never really, talk about two-dimensional surface force. We break it down into components, and we always look at just a normal force or friction, independent from one another. So that means, this guy here is almost never, directly used. But when we have a normal force or friction, we understand that's, there's a contact with the surface. All right. So then you can say that basically we have, like we talked about, right? There's a gravity, right? There's a force, there's a push or pull. But now, for example, let me kind of go back and look at this box. So let's say here's a box sitting there, on some surface, okay? And the question is that, are there any forces acting on it? Well, there are forces acting on it, even if the box is just sitting there at rest. So V equals 0 means that it's at rest. Well, because whenever you have a force acting on it, think of like tug of war, right? So you have an object, or let me do it like this. This is this box. See, if you have one force to the right, and generally what we do here, we use capital F to represent the general force. So let's say if you don't know what type of specific force is this, right? Let's say, for example, if it's a normal force from the surface, we use, lowercase n. Friction, lowercase f, right? But general, let's say, force, we just use F. So let's say there's a force 1. Remember, it's a vector, so I can represent it as an arrow like this. So let's say it says a unit of 10. We'll wait until the unit for next second. So let's say it's 10, and it's to the right, so it's positive. There's another force, let's call this F2, and it's now also 10. Remember, 10 is the magnitude of the force. Also 10, but it's to the left, so it's negative. Then what I can do here is to find net force, where the net force will be the vector sum of those two forces. Now the way I go here is then plus 10, and again I guess it's a good enough time to give you the unit for the force, and it's N, capital N for newtons after Isaac Newton. That's the unit for the force. So let's say it's plus 10 newtons x hat, then plus negative 10 newtons x hat, and since the same magnitude, opposite direction, and there are two vectors, well, we're going to get 0. That means you can have forces that can cancel each other. That box right now has two forces, one to the right, one to the left, pulling the box in opposite direction. But because they cancel each other, right? So we can say then the net force here is 0. Okay. Same thing in a vertical direction, technically. What we have here is this. So I have a gravity force as a force that is always there. Gravity is one force that's always acting on an object, no matter what that object is doing. Jumping, running, sitting there, being pushed, being pulled, and things like that. So let's say the gravity acting straight down, okay? So, and here's an example of that. We call it weight, okay? So pull of gravity on the object, weight. So I put like W with an arrow, okay? But if the box is just sitting there and the gravity acting on it, you don't see anything happening to the box. Why? Because there's also a surface exert force, normal force, as we talked about. And those two also, that means this is only net force in the x direction, and I have to look at net force in the y direction, which is then normal force plus weight. And you can see right there, opposite direction. So technically it's normal force minus weight. And if they are the same opposite direction, same magnitude, opposite direction, they also cancel each other. That means you have an object that is technically right now, it's in statics, what we call, technically we call it equilibrium. All the forces cancel each other and things like that, okay? All right, in any case, so there's a normal force, there's a frictional force, which is from the surface. There's weight, we just talked about, from gravity. Well, there's also now tension. What is a tension? Well, remember I showed you that you can pull something by a rope. That means every time an object being pulled by a rope, then let's say you draw the rope, and then you take that force to be, we call it a tension, and capital T with an arrow. So that's a tension. That means the force that is acting on the object due to some kind of, a string or a rope or a cable, we call it a tension. Again, technically there's a person as an agent acting on it, but we say that it's not a pull, but let's say it's a tension force. That's kind of, if we know it's that force is, kind of transmitted through a cable or a rope or a string, we call that force a tension. All right. Now, what if you have a box, let's say, but you are pulling such that the force here is two-dimensional? Okay. Well, that means imagine that here's the object, right, and being pulled by this rope in that direction. By the way, tension force is always in the direction of the rope. Okay. So let's say that's the force. Well, remember what we do always with two-dimensional vectors. We break it down into components. That means I will always take this force and break it down into x and y components and write down, this equation for the components. That means if I have the F, which is the magnitude of the force, and theta, which is the direction of the force, I can then write, the magnitudes of the, or, like, let's say we can say that the values of the components in terms of that Pythagorean theorem, right? So let's say using the polar coordinates. Now remember, so the best way probably you can do right now is take theta always with respect to plus x axis, right? Then let's say you don't have to put manually any positive, negative signs, but you can always also do that. So let's say here, if this is 30 degrees, and let's say this is 10 newtons, then this becomes 10 newtons cosine of 30. This becomes 10 newtons sine of 30. And then those are the components. That means then what I can do here is I can imagine that instead of being pulled by 10 newtons, 30 degree above the x-axis, then it's being pulled by, let's say, 8.66 Newton in the x direction and 5 newtons in the y direction. Okay, 5 Newton in the y direction. And again, the reason I'm doing this, because things like this, if there was another force acting on it, which is also two-dimensional, I could also break them down into components. So let's say this is, F2x and F2y. And then those two, I can add them together because they're horizontal. Those two, I can add them together because they're vertical. That means you can always take a vector, a force or a velocity and things like that, break down into components. And when you're doing addition of forces, you can then add the components to get the resultant. In this case, it's basically the net effect, net force. So, all right, that's the thing. So that means here is also an example where if you have an incline, like we already covered, if you have an incline, you can tilt your coordinate system. See, we're tilting our coordinate system, and then you can look at everything with respect to this tilted coordinate system. And there is a theta over there, and we will be working a lot with the, let's say, like incline surfaces in this next few chapters, especially in chapter 4 and 5. Because whenever object, moving down an incline or something like that, right, we always have to, tilt our coordinate system. But, remember, it makes our life much easier when we do that, and you will see that when we do all of those examples later on. All right, so again, coming back to this, here's what we do if, for example, our object, okay, which is the box, being pulled or pushed by two forces. Okay, so what are our forces? Here's force 1 and here's force 2. That means two people, let's say, pulling in those directions, F1 and F2. Well, what is the effect of, having those two forces acting on the object? Well, what happens here is this. When you have F1 and F2 acting, then the object then technically affected by both of them combined. It means combination of those. That means, you can say that this vector R, which is then a sum of F1 and F2, is what technically acting on the object. Okay, that means I can just get rid of this and get rid of that, and can say when I add F1 and F2 together, what happens here is this is the net effect. So that's why I call this, let's say net force a lot of times. And a net force is basically will tell you in which direction the object is going to be, let's say later we'll see that in which direction it will be then, accelerating, because force is, what gives us an acceleration. All right, in any case, from here, you can think of, like, let's say when you're doing this, you're going to be pretty much looking at everything else that we studied so far, right, can be applied here. Let's say first thing you're going to do here is you're going to do step 1, which is do a diagram. So this one is known as free body diagram, just short FBD, free body diagram. And we're going to talk about that later in this chapter. So let's say you do a free body diagram, you take the object and put it as a, a point, right? Remember, we can still, consider that as a particle, put it at the center. And you draw those two vectors acting on it. You can say, all right, so here's F1, which is right here. There's F1. And then here's F2, which has a theta 2 angle, right? And then what you do here is you use a diagram to estimate your answer, which is basically do a parallelogram, right? You can do a parallelogram and you can see, right, this is my resultant. That's basically what I have over there, right? Then you do step 2. Remember, what was step 2? Make a table. Instead of calling them vectors, we're going to call them forces. And we're going to call this a force table. Force table. Because I have F1, I have F2, and what I need to get here is net force. All right, so again, this is two-dimensional. How do we get net force? Well, we get only net force, right, from finding its component. Net force in the x direction and net force in the y direction. How do I get net force in the x direction, net force in the y direction? That means basically, how do I get x and y component of the resultant? I'm calling them net force, but you can call them just a resultant, right? Same thing. Well, what you do here is you find x component of 1 and the y component of 1, and x component of 2 and y component of 2. And then just add them together, right? Step 3, which then gives you those equations, right? Equation 1, finding the Rx, which I call it net force in the x direction. That means sum of all the horizontal forces, which will be F1x plus F1y, sorry, F1x plus F2x. Equation 2, then find Ry, which is net force in the y direction. And this is F1y plus F2y, which is adding the vertical component. And that's what we have, right? We need to find the components. So this is what you need to do, right? This is our step 3. We need to find the components. That's why Rx is the net force in the x direction, sum of all the horizontal forces. Ry is the sum of all the vertical forces. Because all I need to do here is find those components. As soon as I find the components, then I can use this to find the magnitude of my resultants. And I can use inverse tangent, Ry over Rx, to find the theta for that resultant. Again, estimate, then make a table, get your equation, and this is technically then part 4, which is finding magnitude and the direction. Okay. Again, this is the same thing we've been doing. Entire vector worksheet, right? All of those things is basically, calculating the net, we call it, like, let's say, a resultant vector, but forces are nothing but, vectors added together. Okay. So it can sometimes get a little bit complicated when you have 2, 3, 4 forces acting on it, some of them different direction. But again, all you have to do here is just follow this, steps, and no problem. Doesn't matter if it's like, multiple, let's say, forces acting on it. All right. So let's look at then in terms of some of the Newton laws. Okay. So the Newton's first law, Newton basically gave us 3 laws of motion. So the first law, in a way, is a description of uniform motion. Okay. That means what happens when an object is basically not moving or moving at constant velocity, straight line. That means, object has a uniform motion. Okay. Well, the way he explains this, Newton's first law, it's pretty much like this. If you have an object that is at rest, okay, this object going to continue basically be at rest. Or if you have an object moving in constant velocity, that means it's going to continue moving at constant velocity unless there is some external force acts on it, right? So think like this. So if you have an object just sitting on the table, right? So let's say that's a table, like object sitting on the table. I don't know. Maybe like your pencil box or something like that, or your calculator. Well, this object here is at rest. And what we, basically gonna call this, we can call this is an equilibrium. You're gonna see in a minute. So let's say this is an equilibrium. What does it mean, equilibrium? Well, it means that either there are no forces acting on this object, or when there are forces acting on this object, they all cancel each other. And object is in equilibrium, okay? So, and when you, let's say, exert some kind of external force, let's say finally somebody's just pushing this box, right? That means this is this is something that cannot be canceled anymore, right? Then this force, for example, can make the object, move. That moving, like it's gonna make it like accelerate. But unless, let's say, this force is there, right? If this force is there, yes. But if there's no forces external like this, sometimes I call this F external, right? But let's say if there are no external forces and all the forces, cancel each other, then object is going to be, sitting there in equilibrium. All right, so that means in a way you can say that here's, for example, you have a hockey puck, right? So you have, you strike it with, from 2 different directions, right? Let's say you take 2 hockey sticks, strike the puck from 2 different directions. Here's, force 1 from the, stick 1. Here's force 2 from the stick 2. But what we do here is, if I look at F1 and F2, I can see that both of them horizontal, both of them in same magnitude in opposite direction. If assuming that in the same magnitude opposite direction, then if I calculate this, I'm going to get 0. In a y direction, I get 0 because there are no vertical forces, for example. That means x component of this force and y component of this net force is 0. And when the x and y component of the net force, both of those components are 0, then we can say the pack is in equilibrium. And when something is in equilibrium, it does not accelerate. I mean, what is acceleration? Well, acceleration means that it doesn't change its speed. It doesn't slow down, or it doesn't speed up, or it doesn't change direction. That means if it already was at rest, it's going to continue being at rest because its initial velocity was 0, so it's not going to change its velocity. It's going to continue being at rest. But if, for example, if somebody's velocity is 3 meters per second x hat, well, it's going to continue moving at the same speed, same direction, without changing any of the properties. So that's what the Newton's first law tells you. That means it tells you basically condition of equilibrium, which is basically uniform motion, right? So why do we have a uniform motion? Because the object is in equilibrium. What does equilibrium mean? It means that all the forces in x direction cancel, all the forces in y direction cancel, which means that those are the components of the resultant or net force. And if the component of the net force is 0, that means the net force itself is 0. Okay. Well, here's what, important thing, kind of like, let's say that a little more advanced, we just, kind of like mention it here. Generally, we have what we call a frame of reference, okay? So there's what we call inertial frame of reference. An inertial frame of reference is a reference frame, right? Like a room or something like that, where Newton laws basically are obeyed. That means all Newton laws are valid. That means, for example, if I'm doing an experiment in my room and I put an object in, on the ground, and all the forces acting on it, and let's say all the forces acting on it, which is, let's say, a surface force up, gravity down, nobody's pushing or pulling, right? An object is going to continue being at rest. That means that Newton's first law is obeyed. This room here is an inertial frame of reference. All right. So if I go to another place and do the same thing, right? Put the object on the ground and nobody's pushing or pulling, just the surface force upward and gravity down, and it just sits there at rest. All right, that's an inertial frame of reference. But for example, if I take the object somewhere else where I put it on the ground, and then I see that the object starts sliding up, backward or upward, even though nobody, seems to be pushing on it, then it's not a valid, reference frame. So for example, which one is a not valid reference frame? Well, it could be, for example, I don't know, a bus, right? So think like this, you're in a bus, okay? And when the bus is at rest, so let's say you're standing in the bus, bus is at rest, you put a ball next to you, I don't know, like a bowling ball or a soccer ball. Well, if the bus is at rest, you put the ball next to you on the ground, you can, predict that, the ball is going to be just sitting there at rest. And you should be correct, right? Because if the bus is at rest, let's say velocity of the bus is 0, then the ball here is just sitting there. But most of you probably can, intuitively imagine what happens when the bus starts speeding up. So that means there's acceleration. Think like this, what happens when the bus starts speeding up forward? Well, the ball is going to start sliding backward, right? Nobody's pushing, nobody pulling, but it's, as soon as the bus starts, speeding up, right? The ball rolls backward. When the bus starts, slowing down, hit the brake, the ball gonna roll forward. Again, nobody's pulling or pushing. Well, that's a not example of an inertial frame of reference, and means that any reference frame that is at constant velocity or in equilibrium, right, is an inertial reference frame. But any reference frame that is accelerating, like the bus starts speeding up or slowing down or change direction, right, is an example of non-inertial reference frame, right? That means Newton's first law is not obeyed, so the frame of the airplane or the bus basically not, inertial. Okay. That means what we're going to do here is we're going to assume that we're always dealing with inertial reference frames. That means we're always going to assume that either, you know, we're in a bus that is at constant velocity, or we're in a room that is constant, you know, they're not moving, right? That means always going to be an inertial frame of reference. That means all the Newton laws will be obeyed. Okay. Now, the question now is this. All right, so we got the first one, where if you have an object that is moving with some velocity, right? And if all the forces acting on it is going to continue moving with the same velocity forever, basically. Okay. That means, you know, if you have, you can see, right? You have a pot moving on ice and all the forces cancel each other, then it's going to just move like that. But what happens when, as I said, right? What happens when there's an external force acting on the object? For example, it's moving, but then you know, also start pushing. Or maybe like, let's say it's at rest and you start pushing. Well, when you start pushing, then what you do here, you exerting force that is not canceled by other forces. That means, for example, in the x direction, you can see, right? This is the only force, only force, only force. That means that force is the only force in the x direction. So when I have the, remember the components, net force in the x direction, net force in the y direction. For example, in the y direction, there's still going to be zero because I have normal force from a surface and gravity, the weight, cancel each other. But see, in the x direction, I have just one force over here, but nothing to cancel. So I have non-zero force in the x direction. That means this is no longer zero, for example, at least, you know, in this case. What does it mean then? Well, it means that this non-zero force is going to make the object accelerate. So that's what the force does to the object. When there is a non-zero force, then the object will accelerate. And object acceleration is in the same direction as the net force acting on it. And since the net force is only in terms of the forces in the x direction, or that one force, then it's going to accelerate in the same direction as force. And what we have is this. Force is then proportional to acceleration, or we can say acceleration is proportional to the net force. So that means, you know, if I push twice as hard, right, you're going to get twice as much acceleration. You know, 10 times as hard, 10 times more acceleration, thing like that. That means acceleration is directly proportional to the magnitude of the force that is applied. Well, same way, now what we're going to do here is we're going to introduce something else that is proportional to the acceleration that affects how the acceleration quantity, the value of the acceleration can be calculated. But this time, this is due to the fact that the object that we have, that we're considering, right, can also have mass. And then the mass of the object now is a factor, where in chapter 2 and 3, 1, 2, and 3, we didn't care about the mass. Here we care about the mass now. It's a quantity that we are now starting incorporating into our equations. And the mass has the opposite effect of the force, where the force is directly proportional to the acceleration, while mass is inversely proportional. That means acceleration is, you know, decreasing, right? It's actually smaller if you are, you know, dealing with a heavier object. So think like this. If you have like a light chair, you give it a little bit of force, a little bit of push, and it's going to just change its velocity by a lot because it's just a light, you know, chair. But try to do the same thing to the table. Table is much heavier. So when you same push you do that to the, you know, you apply to the table, well, it's not going to change its, you know, velocity so much because of that force, because it's much heavier. That's why acceleration is inversely proportional to mass and directly proportional to force. So then what we end up, we rearrange and we get this, probably the second famous physics equation, F equals ma, right? So hopefully you know which one is the first, you know, the most famous, you know, physics equation. Probably is an equation that most of the people don't understand exactly what they represent, but I'm sure everybody knows M equals mc squared, okay? So, but, you know, let's say this is something we're going to be learning in physics 7, at the end of physics 7. In this chapter, it's the second famous physics equation, F equals ma. That means when you apply force, the object will accelerate, but its acceleration will also depend on how much mass the object has, okay? Lighter object will accelerate much more, heavier object will have a lot less acceleration. But every time there's a force acting and there, let's say non-zero net force, think of it like that, non-zero net force, the object will accelerate. So that's why object can speed up due to that acceleration, or it can slow down due to that acceleration. So over here, if you have an object moving to the right and you push to the right, it's going to speed up to the right. But if you have an object moving to the right and you start pushing to the left, then you actually make the object slow down and maybe stop eventually. That means direction of acceleration is directly proportional to the direction of the force acting on the object. It's proportional to the net force acting on the object. All right, so then this is basically our second law, Newton's second law, which means that, very simple, it's F equals ma. Net force equals ma, which means that every time object is under non-zero net force, it's going to accelerate. And this is example where here's the acceleration where it changes with the mass. See the m1, you have the same force acting on it, but see m1, which you can see from equation 2, right? So let's say you have a 10 Newton force acting on a, let's say a 1 kilogram object. Well, this is then 10 meter per second square acceleration. But let's say then acceleration when saying 10 Newton acting on a, let's say 2 kilogram object. Now you have 5 meter per second square acceleration. You can see, right, you double the mass, you half the acceleration. Well, how about now this acceleration acting on a 5 kilogram object, for example? Well, now you have 2 meter per second square. You can see, right, bigger the mass, smaller the acceleration. Now, F, the force, equals mass times acceleration, ma. Mass has to be in kilograms, acceleration meter per second square, and when the right side of the equation is kilograms times meter per second square, then we can say that the left side, the newtons, which is for the force, and this is in newtons, is equivalent then to kilograms times meter square. So you can say 1 Newton is equivalent, to pushing a 1 kilogram object and give it an acceleration of 1 meter per second square. All right. Now, we're going to look at some of the different type of forces, and we're going to try to understand, specific ones, let's say, because when you talk about force, right, you can have force due to a very specific agent, earth, surface, a person, right? Those type of things. So each one going to be labeled a little bit differently, because when you have remember when we had, for example, the vector addition, so we label them as A, B, C, D, right? To, distinguish them so we can understand which one is what. Here with the forces, you don't want to put like, they're all, like let's say in terms of just F, right? And even F1, F2, F3 is a little bit confusing. But for example, if you know that this is force of gravity, then you can actually put W, which is for weight. And then you know that if you have a then diagram and you put the arrow with the, W weight, right? You know that force is due to, let's say, gravity. That means instead of putting like F1, F2, F3, which is not very clear who's the agent, we put like, let's say N for the normal force, W for the, weight, which is gravitational force, right? Or T for the tension, which that means it's some kind of rope, and all of those things. Now, important thing here to understand is this. The weight, which is a gravitational force acting on the object, is not the same as the mass of the object. Mass is basically, you can see that is an information about how much matter the object has, how much material, how much electrons and protons and everything the object has. And the mass is given in terms of units of kilograms. Weight is basically, your gravitational force, the magnitude of the gravitational force acting on it. And we can calculate weight, the magnitude of the weight, by taking the mass and multiplying by 9.8, which is gravitational acceleration. Remember, what is the force? General equation, mass times acceleration. So if the force happened to be weight, so it's mass times gravitational acceleration, which remember is G. So mg is always then for the magnitude of the weight, which is a gravitational force. Now, one thing we have here is this. The mass is a universal quantity, which means if this object, for example, is 1 kilogram, it's going to be 1 kilogram everywhere. everywhere, Earth, Moon, and Mars, and Jupiter, go take it to Andromeda Galaxy, it's going to be 1 kilogram. Weight is different. Weight of this object will be its mass. So this is weight on Earth. So its mass, which is 1 kilogram, times the g for Earth, which is 9.8 meter per second square. Then I get 9.8 newtons. So that's what I have. See, the weight is 9.8 newtons. Because g, which is 9.8, is very specific to Earth. G, for example, other places, like let's say others, celestial places like Moon, Jupiter, Mars, something like that, right? It's different. Okay. So that's why what I have here is 1 kilogram object is 9.8 newtons on Earth, as in terms of its weight. 1 kilogram object taken to the moon, it's still going to be 1 kilogram. But g for the moon is 1.62 meter per second square. So then weight will be 1 times 1.62 or 1.62 newtons, right? That means you can see, right, your weight changes. So, object lost weight. Well, it didn't lose weight, it just happened to have a weight over there based on the gravitational acceleration for that location, which is for the moon. And that's what we have. You have to look at it in terms of this, in terms of the g is different everywhere. And then weight will be different depending on that quantity g. Mass doesn't depend on g, it's just intrinsic property of the object, and it's going to be then the same everywhere. So then you can calculate that. Sorry, you don't calculate, right? You just measure it, right? And you can assume that you measure the mass on Earth. You can then assume that everywhere this object is going to be, same mass. All right. All right, so then in a way, this is basically, you can say, right, this is how we measure. Let's say you take an apple, put it on a mass balance, and then find its mass. And then you can always assume that that's basically the same mass, right? And since gravity is constant, we can compare forces to measure unknown masses and things like that. So unfortunate in this type of, class, right? We never get to work with, instruments and things like that. So we actually do use this type of mass balances a lot in our, experiment, in-class experiments. All right, so we got Newton's first law, remember, which was basically equilibrium. That means object at rest going to continue being at rest until some kind of external force pushes or pulls, which is basically, uniform motion, right? Equilibrium. We can call uniform motion as equilibrium right now. Then Newton's second law tells you what happens when the forces don't cancel each other, right? So that means, you take there's, something, some kind of box next to you or the chair, you just push the chair, you're going to see that, it changes velocity. Because, for example, if the chair right now next to you is at rest, its velocity is 0. In order to change the velocity, which means to give it an acceleration, we have to apply force. And if you push it, that force gives it an acceleration. Okay. Now, Newton's first law and second law pretty much works kind of similar way. You take one object, and then you look at forces acting on that object. That means things like this. So here's my object of mass m. So let's say if I have force 1, 10 newtons x hat, then let's say force 2, negative 10 newtons x hat, for example. And then let's say there's a normal force and there's a weight, right? And then I look at forces in the x direction, I add F1 and F2 together, get 0. I add vertical forces, normal force and weight, let's say, then I get 0. Then I can say, right, so this object here is in equilibrium, which means that, the object here, if it started with rest, then it's always going to be at rest. But if it starts with, let's say, some kind of 5 meter per second velocity in x direction, it's going to always then continue moving with the same velocity, same direction. That's what equilibrium means. By the way, this type of equilibrium, when object is at rest, remember, equilibrium pretty much means this: no acceleration, and forces cancel each other. So when you have acceleration 0, so technically like this, when acceleration is 0 and velocity is 0, This is known technically as static equilibrium. So static equilibrium. This is static equilibrium. But for example, here, acceleration is 0, but object doesn't have a 0 velocity. That means it's moving, right? It's moving, but it's not accelerating, not speeding up. This is, sorry. So this is known as a dynamic equilibrium. So dynamic equilibrium, which means that it is equilibrium. Again, equilibrium means the object is not accelerating, but the object is moving. It's not at rest. It is moving with some velocity, and the difference between dynamic equilibrium and static equilibrium is just that. Static equilibrium, no acceleration and object is at rest. Dynamic equilibrium, no acceleration, but object is moving. This is first law. Second law is just, in a way, thing like this. The difference here is that you come back and say, you know what, this force here is 20 instead of 10. Well, if that force is 20 instead of 10, then what do we get? Well, we don't get like equilibrium anymore, because in the x direction, right? Let's say make this as 15, for example, 15 newtons. Then in a y direction, they still cancel each other, but in the x direction, then they don't. 15 minus 10, you get 5 newtons. Well, if you get 5 newtons, then acceleration in the x direction, which is net force in the x direction, now is going to be 5 newtons divided by the mass. In a y direction, net force in the y direction over m, this is the acceleration in the y direction, so this is going to be 0 because net force is 0. But then you can see, right? So let's say if it's a, 1 kilogram object, then object now has 5 meters per second square acceleration in the x-head direction. That means this object is going to start speeding up in a horizontal direction. But again, Newton's first law or second law takes one object as object of interest. That means you're looking at the box, and then you're looking at all the forces acting on the box. You ignore everything else. You have, okay, so this is my box, or 1 kilogram box, and I want to know how many forces acting on it, in which direction, and how I can then find the net effect. That's an example of first law and then second law. Looking at what happens to one object to all the forces. If all the forces cancel each other, object is in equilibrium. If the forces don't cancel each other, then object is basically accelerating. Just that, either equilibrium or acceleration. Now let's look at third law. Third law is a little bit different, because the third law talks about what we call interaction between object and its agent. So let's say, and it just basically tells you this. For example, if here's my object, well, then every time this object has a force acting on it, so let's say the surface, right, gives it a normal force. So let me do it like this. So this is basically the force that surface exerts on object. SO, surface on object. Well, we call it normal force, right? But here's the thing. When the force acting on the object from the surface, that means the surface exerts force on the object, exactly same time, object then exerts force on the surface. And this force is in the opposite direction, and this is the force that object exerts on the surface. How do we know that? Well, think like this. If there was something right, below the object, right, over there, or the surface is, fragile, right, you put the object there, it can actually break because it exerts force. It's pushing the ground. So that means this force that, surface exerts on object and force that object exerts on the surface, those are known as action-reaction forces. And Newton's third law technically can be described as this. For every action, there is an equal and opposite reaction. That means this force the surface exerts on object, and force that object exerts on the surface, they have the same magnitude, but they have different directions, opposite directions. Same magnitude, but opposite direction. That negative basically represents that. Let me there you go. That means if you are here let's say I'm pushing the box in this direction. So this is a force. So push force on the object or person on the object. Then the object exerts force on the person, object on the person. Okay. Again, every action, there is equal opposite reaction. So for example, here, you are given picture of an athlete, right? There's one of those Winter Olympics, and he's shooting a gun. Okay. So what happens here is this: in the gun, then basically has a bullet inside. So when you shoot, then there's interaction between the bullet and the gun. Okay, like let's say the rifle and the gun. So what happens here is this: so the rifle hits the bullet, the mechanism side, right? And the bullet is being pushed to the right. So this is a rifle pushing bullet to the right, and the bullet is then pushed to the right. But at the same time, when the rifle pushes the bullet, bullet pushes the rifle in the opposite direction. This is the bullet on the rifle. And if you ever shot a rifle, use the rifle, you will see there's a recoil. You shoot a bullet, the rifle goes backward a little bit. There's a recoil. Why? Because the bullet is actually, pushing the rifle backward. So that's why, for example, because of their relative sizes, right? Bullet is tiny, rifle is much bigger and heavier. The rifle just goes backwards a little bit, but bullet, flies to the right with much higher speed, but still, that's an example of action-reaction forces. And, you can see that any force is, pair of, action-reaction, let's say force. So you can see, right, you have an apple on the table. So the table exerts force on the apple exerts force on a table. Okay, so think like this. So this is my object, which is the apple. If I look at just the apple itself, I have two agents acting on it, acting force on it. Surface upward force, table and apple, and earth downward force, because earth always pulls things down. Like basically it's an attractive force toward earth. But then if I'm looking at just this force that surface exerts on the apple, then I can, or just this force which earth exerts on the apple, then I can find the reaction of those forces. Because this one, right, which is earth on the apple, exactly same time, then apple exerts force on apple exerts force on earth. And if I'm looking at this, which is the table on apple, well, there's a force that apple exerts on the table. Okay, that means all of those are, action-reaction pairs. Okay, every single force. And that's why here I'm not just looking at one object, I'm looking at interaction between two objects. So that's why Newton's third law is slightly different, right? Slightly different. And it's looking at in terms of, if you have an object, we have one force acting on it, then object at the same time exerts force on the other, thing. That means, object and agent always exert force on one another. But if I, let's say, don't care about forces that object exerts on other things, I can just concentrate on the object and just look at only forces acting on the object and see how it's moving due to those forces only acting on the object. So that's basically what we do in Newton's laws of motion number 1 and number 2. That means if I'm looking at the application of the first and second law, I'm only looking at what happens to the object due to the forces acting on it. And I ignore all the reaction forces that it exerts on other things. All right. Next, we have this free body diagram that I mentioned. And the free body diagram is technically going to be very useful. So, and this is something we already been doing, which is, drawing our vectors, right? So, but here we're going to be then being, again, very careful. Whenever we have an object has forces acting on it. So we're going to take object, put it at the center of our coordinate system, and then start drawing the forces, with labeling, what type of force and direction and things like that. So for example, here we have a runner, so you can see, right? So, and the force acting on her due to this over there, right? So we can see, right, that there's a block over there. So then the force of the starting block on the runner has a vertical component because this force acting like this, normal to the surface. You can see, right, there's a little bit of tilt at the surface. So this is the force acting on the runner. So then what we can do, we can break it down into components, X and Y components, okay? That means normal force, important to understand, is always perpendicular to the surface. If your surface is flat, then it's straight up. If your surface is, you know, kind of like inclined like that, then here's no, you know, that normal force, all right? Or the, you know, surface force, you can think like that. So that's kind of what we have. That means we take this force from the surface, it's a two-dimensional, we break it down into X and Y components. Gravity, always acting straight down. And remember, gravity is one force that's always acting on the object. And here's, for example, you have a player that is, you know, basketball player that is in the air. And when the player is in air, then he basically in free fall. Remember, jumps, as soon as he jumps, he's in free fall. And one force that acting on the object when in free fall is gravity, the weight. So we just basically, okay, so here's our object, we make it as a particle and say there's a downward force of gravity. And here's a second player over there. The second player is, you know, on the surface. So that means other than gravity, which always acting, right? There's also a surface force. Okay, so that's why he's not in free fall. That means not affected by gravity, because surface force cancels the effect of gravity, and the object here is in equilibrium, where the jumper is in basically free fall. It is, you know, slowing down, right? It is, you know, actually accelerating in a negative direction. So it is actually slowing down. So you have equilibrium and, you know, Newton's first law on the right side for the player, Newton's second law on the left side of the player. Okay. Let's do some examples here. So here we have a car that is towed to the right at constant speed, which is the correct free body diagram. And you give it like a picture like that. So what we do here is, you know, we always have a coordinate system. This is X, this is Y. And you take your object and put it at the center of your coordinate system. Right. And then you draw the forces. Right. So what are the forces that we have is this. So there's a, you know, a string. So I can say then, all right, so there's a tension force, right? A tension force to the right in the direction of the rope. Also, what I have is this. Well, the car is on the surface. So there's a normal force upward. Like that. And gravity, right? Because it has a mass. So the gravity acting on it and it's downward. Okay. So then if I'm looking at the net force in the X direction, I have tension for now, and net force in a Y direction, then I have normal force plus weight. But since they're in opposite direction, I have normal force minus weight, so they cancel each other. But in the X direction, see, I have tension there. Does it mean that, you know, if this is just a tension, so it's equals to mass times acceleration? And the question is, does it mean that my system is accelerating? Well, no, you have to read the question carefully. It says it's being towed at constant speed. Constant speed means this is in equilibrium, dynamic equilibrium. That means tension cannot be the only force in the X direction. It means there's another force, which is from another, again, from the surface. It's a friction force, remember? Then it's in opposite direction. Then T minus F, again, I get 0. That means if it's in a constant speed, if my object is moving at constant speed, that means all the forces have to cancel each other. And that's my free body diagram. That means I have two vertical forces that should be more or less same, you know, same size, opposite direction, and two horizontal forces, opposite direction, you know, same size. Okay. Here's another one. You have a car is parked on a hill. And want to draw the correct free body diagram. All right. So I draw a car on an inclined hill, right? And, you know, we do the coordinate system like this, remember? All right. So y-axis, positive x-axis, and I'm gonna take my car and place it here at the center. Okay. Now the free body diagram tells me that the picture tells me that there's a surface force, normal force perpendicular to that because it's upward, and it's basically on the surface. Well, gravity acting on it. Well, in which direction is gravity acting on it? Well, it's always straight down. Okay, and this is theta, which is inclined angle, always happen to be that angle over there. So now what I have is this. See, if I if I'm looking at the net force in the x direction, so let's say, think like this, if I make this table, right, that I have. So here's normal force, here's weight. These are my forces, x components, y components. So think like this, the x component, the normal force has no x component. It has a y component, it's upward in a positive y direction. Weight, in this case, actually is a two-dimensional vector. So I have to break it down into components. So here's the y component of the weight, and here's the x component of the weight, right? So break it down. You can see this theta here is this theta over there, which is, you see if I move the x component here, x component end up being adjacent side, sorry, opposite side of the triangle. So it's actually weight of sine of theta. It's a, y, let's say the x component is the opposite of the triangle, so it's in terms of the sine of theta. And it's down in a positive x direction, so it's positive. Or you can say it's a fourth quadrant, so x is positive. Y component is then will be w cosine of theta. W cosine of theta. And fourth quadrant tells me that it has to be negative, the y component. Now, think like this. If those are the only forces I have, then this is net force in x, this is net force in y. Okay. Now the question is that, is my system accelerating or is it in equilibrium? Well, you have to read that from the wording. It says it is parked. Parked means it's in equilibrium, which means then technically this has to be 0 and this has to be 0. You can see that in this y direction, so technically you can say it's normal force minus weight cosine of theta, they can cancel each other. But in the x direction, you have just x component of the gravity, which is w sine of theta. And you cannot have that, by itself cancel it, let's say and get 0. That means there's another force there. Again, that force here is, in this case, is the friction, and it's acting in a negative x direction. It's basically acting like that. Think like this, friction always acting sort of like, let's say, in potentially opposite direction of the motion. That means if the object is moving to the right, friction acting to the left. Or if the object here is, potentially can move down the incline in this case because gravity will be pulling it down, then it will be acting to the left, upward. That means it's always opposing the motion. So that's why it's always going to be opposing. And in this case, see if you do minus friction, you get 0. Now it makes sense. So then this is my free body diagram. Okay, because there are two forces in x direction canceling each other, two forces in the y direction canceling each other. All right, so basically now we have just a bunch of examples that we can see in terms of what happens. You have a 1.2 kilogram lies on a table. The book is pressed down from above with a force of 15 newtons. What is the normal force acting on the book from the table below? That means what is the normal force? What is the magnitude of the normal force? Well, what we do here is, again, we make a free body diagram. X to the right, y up, right? And then, the X is horizontal, Y is vertical. There is no incline, so it's a general flat surface coordinate system. And what I have is this. The table here is a particle at the center, right? And we drew all the forces acting on it. Well, there's a normal force from the surface, which is upward, perpendicular to the surface. There's a gravity, right? Weight, downward. But there's also, right? So there's a, it's being pressed down, which means when you press down, you exert force down. And that's what this force is. That means you have two downward forces and one upward force. But here's the thing. Think of like, if you take a book, put it on the table and press it down a little bit, what happens to the book? Is it accelerating? No, right? It's just still sitting there. That means F net here is 0. That means what we do here is we make a table again. Basically, we do the free body diagram and then make a table. These are my forces. And these are going to be X component and Y components. All right, so how many forces do I have? I have 3. I have normal force. I have this applied force. I have weight, right? And some of those 3, right? So technically, right, my F net is what? So the F net, you can write it like F sub net or just, sum of the forces. The same. This is also not F net. Is equals to just N plus the applied force plus weight. But since this is the vector format, remember, we don't just add them together, right? Or this, like not, generally. But what we have here is this. Here's the net force. What I can do here, I can see that N has no X component, is in an upward positive direction. F has no X component, is in a downward direction. Weight has no X component, is in a negative Y direction. That means there's nothing in X direction. But I'm also told that since F net is 0, that means there's also nothing in a Y direction. That means when I take this and put it in equation, net force in a Y direction, because nothing in X, so there will be normal force minus F minus weight equals 0. Because I have one upward force, two downward forces. That means, N is positive, F and W are negative. So when I'm adding them together, it's basically same as N minus F minus W, which means this, N is equals to F plus W. Now, what is W? Remember, W is mass times gravitational acceleration, it's F plus mg. That means that normal force is equals to, the force, which is, remember, we're given is 15 newtons, plus an mg, which is 1.5 kilogram object times 9.8, meter per second square, right? So if I get those, then I can calculate what's the, the force acting on it. So let me do. So 15 plus 1.5 times 9.8, I get, 29.7 newtons. So that's my normal force. It means I could calculate that from whatever was given to me. All right, so here's another example. You have an orangutan weighing 500 newtons hangs from a vertical rope. What is the tension in the rope? Now we want to find the tension in the rope. All right, so here's a pictorial representation, just orangutan basically hangs from a vertical rope. And here's the, again, it's important to understand the wording in a problem. When it says hangs, well, what does it mean? Well, it means that it's in equilibrium again. It's in, a static equilibrium, which means that if I take orangutan and put it in my center of my coordinate system, I have two forces acting on it. Two forces, they have to be two forces, right? So they can cancel each other, so it's in equilibrium. One is always going to be gravity, which is down. Well, the other one is, tension, because, rope is what basically keeps him, him or her, like, let's say, hanging like that. And what I have here is this, let's say it's simple enough. You can see, right, that you have two forces, means that the net force is equals to tension plus weight. That's, that's how you write it in vector format. But you can see, right, this is basically, only in a y direction. So you can say that, all right, so this is then tension, y hat minus weight y hat, right? Both of them are, y hat direction, but one is positive, the other one is negative. And this is equals to 0 because it's in equilibrium, it hangs, which means tension is equal to the weight. And we were already given weight as 500 newtons. That means tension is also 500 newtons. Right, it's simple enough, but it's important to understand some of those wordings. All right, so we have another example, and this is actually an application of Newton's second law. And then we can see, let's say, how we can use Newtonian dynamics with kinematics of the previous chapters. All right, so here's what I have. A Boeing 737, a small short-range jet with a mass of 51 kilogram, sits at rest. All right, the pilot turns the pair of jet engines to full throttle, and the thrust accelerates the plane down the runway. After traveling 940 meters, the plane reaches its takeoff speed of 70 meters per second and leaves the ground. What is the thrust force of each engine? All right. So you can see that here's sort of like, let's say, a picture of this, an example of the picture, right? And what we have is this. It's asking for the force. And we're given the mass. remember what I have here is this, right? Force equals mass times acceleration. And you can see this is just one dimensional. So it's moving in the x direction, right? So net force equals mass times acceleration. So it's good enough. And I have the mass. All I have to do is just, multiply by the acceleration and I have my net force. Well, the problem here, we're not given the acceleration. So I don't know what the A is. And I have just one equation for the net force. What are we going to do? Well, here's the thing. You have one equation for the net force, which is net force equals mass times acceleration. But you have a number of equations to find the acceleration using the kinematic equations. Because here's what we have. We are given that, let's say taking from x initial, right, which is 0, we know that it starts from rest. So v initial is 0. And then we know that it travels 940 meters, which is x final equals 940 meters, right, until it reaches final speed of 70 meters per second, and it's ready to then take off. So what we want to find here is net force, but technically, right now I need to find acceleration so I can find a net force. And I'm given all of those things to find the net force. And obviously what I have here is, well, I'm given more than enough information to find acceleration and then use that to find then the speed, the force, net force. That means I'm going to be using this to find, acceleration of the object using the kinematics, and then use that with the, let's say equation of the dynamics. And that's what we're going to do. A lot of times, things like this. This is dynamics, and then this is kinematics, which is equation 1, 2, 3, and 4. Okay. And the link between them, which is link between dynamics and kinematics, is the acceleration. Because remember, other than equation 4, which we can kind of like ignore right now, right? All the other equation 1, 2, and 3, well, they have, the acceleration. Equation 1, v final equals v initial plus at. Equation 2, x final equals x initial plus v initial t plus 1/2 at squared. Equation 3, v final square equals v initial square plus 2 times acceleration times delta x. That means I have those 3 equations that I can use to find acceleration. Then once I have acceleration, use that to plug in there and calculate the net force. The question here is, which one can I use? Well, remember, one information from the given vol table, right? You can see that we're not given, and that's the time. That means I cannot use any equation of the acceleration with time. I cannot use that. I cannot use that. That means this is the only thing I can use. Okay, so let's use that then. V final equals V initial plus, like that, right? Plus 2 times A delta X. Which means I can rearrange this and solve for acceleration, which will be V final square minus V initial square divided by 2 delta X. And plug in values, right? So V initial is 0. V final here is 70 meters per second square divided by 2 times 940 meters. And acceleration is going to be then 2.61 meters per second square. All right, I got that. So what I do here is I go back to this equation for the mass times acceleration for the net force and say it's 51,000 kilograms times 2.61 meters per second square. And I'm going to get 133,000 newtons. Okay, so that's what I have. But this is the acceleration of the plane with 2, right? So let's say 2 engines, pair of jet engines. And it's asking what is the thrust force of each engine. So what I do here is just basically, understand that this is due to the 2 engines. That means, the net force, which is the thrust force from each engine here, is then half of that. Well, roughly, 67, and put it like this, kilonewton. Remember, kilo stands for 1,000. That means 67,000 newtons. All right, so that's what we do for this problem. That means you can see, right, you can always go and use kinematic equation to find acceleration and use that in a dynamics, or you can use dynamic equations to find acceleration and then use that acceleration to find, you know, any of the kinematic quantities, position, velocity, time, and things like that, right? So let's say things like this. If you were given this information, then I would have used this to find acceleration, and could have used acceleration to find any of the other qualities. So for example, the time, how long does it take, right? All of those things. All right. Here's another example here. This example then goes like this. So when a rubber band is stretched to pull on a 1 kilogram block with a constant force, the acceleration of the block is measured to be 3 meters per second square. When a block with an unknown mass is pulled with the same rubber band using the same force, its acceleration is 5 meters per second square. What is the mass of the unknown block? That means you have 1 kilogram block with the same force gives you 3 meters per second square acceleration. Then some unknown block with the same force gets 5 meters per second square acceleration. So what we want to know here is, what is that unknown mass? Here's the thing. One reason I have this example here is that I can show you that sometimes it's better to solve problems using what we call a ratio. So here's one thing that both of those blocks have in common, the force, right? I can say force on block 1 is the same as force on block 2, correct? Then I know that force is nothing but mass times acceleration. It's mass 1 times acceleration 1. And this is equals to, for the force 2, which is mass 2 times acceleration 2. Then what I have here is this. Remember, I want to find acceleration, mass 2. Well, then I just divide both sides by, let's say, acceleration 2. Cancel this, and I have mass 2, which is the ratio of m1a1 divided by a2. Then m2 is equals to 1 kilogram times 3 meters per second square, then divided by 5 meters per second square. You can see, right, meter per second square cancels out, and you have then 1 times 3 divided by 5. Kilogram is the only unit surviving, and we get 0.6 kilogram. Okay, that means you can just use the ratios, right? Understand that, you know, one thing that you have in common is the force. Well, one thing you could have done, you could have calculated the force and then used that, but you can also use this ratio and be able to calculate things, you know, directly without solving for the force. All right. So here's then generally what happens. Every time there's a two-dimensional problem, right, you have to understand that if you have your object here, right, so let's say here's a boat being pulled by 2 people, and what you have here is, let's say you have force A, 40 newtons, 45 degree, you know, with respect to positive x, and force B, 30 newtons, 37 degree below the positive x. And then what I have is those forces then make the boat basically accelerate to the right. So the way you approach this is draw a sketch. Then for one object, draw a free body diagram, which is then you decide which one is your object. Is it the boat? Is it object A, or the person A, or person B? Well, let's say the boat. So then you take the boat and use the free body diagram. That means you only take your boat as an object and put it at the center. And then you say, all right, so there's force A and force B acting on it. But then you have to understand, right? A and B forces, force A, force B are two-dimensional forces. We don't like working with two-dimensional forces. What do? We break them down into components. And you can see, right? Components of A in the X, components of Y in the X. Components of B in the X, component of B in the Y. Now I can add those two together because they're both in the X direction, and add those two together. That means this is basically what we've been doing, okay? So that means we do the free body diagram, we label everything, right? And then from that, we pretty much do the same thing as we found, did before for the, those vector additions. We find, the resultant magnitude. That means you want to find resultant y and resultant x. All right. So apply second law to each component, right? And calculate that. That means you want to find, basically, remember, this is step 1. Then you can do step 2 where we put everything in the table. Step 3, then you get your equation, net force in the x direction, net force in the y direction. Then for the step 4, right, then you get equation 3, which will be then magnitude of the net force, which is in terms of the component squared, right? Net force in x squared plus net force in y squared. And then, equation 4 gives you then direction. Inverse tangent of net force y over net force x. Then you have the direction and magnitude. It means your goal will be, in order to find f of r, the resultant force, and the direction, you first, break every force A and B into components, use those components to find the component of the resultant. Then you go into equation 3 and 4 and solve for the magnitude and direction of the resultant. That means all of these things basically going to be pretty much the same. Right, and solve. All right, so let's look at an example, kind of like very similar to one. A hockey puck having a mass of 0.3 kilogram slides on the frictionless horizontal surface of an ice rink. 2 hockey sticks strike the puck simultaneously, exerting the forces on the puck. Then the force F1, we're given in the diagram, has a magnitude of 5 newtons, and the F2 has a magnitude of 8 newtons. Determine the magnitude and direction of the puck's acceleration. All right, so we're given 2 forces acting on the puck in terms of their direction and magnitudes. And then we're going to basically, find acceleration. All right, so here's then what I have. That's already my free body diagram. This was step 1, free body diagram. The next will be step 2. Step 2 will be like this. Doing the vector table, the force table. I'm going to call it force table. My forces, x component of my forces, y component of my forces. What I have here is I have F1, I have F2. What am I going to get from those? I'm going to get net force if I add those 2 together, right? And that means I'm going to try to then use them to get x component of the net force and the y component of the net force. And the way I do that, I break down each force into their components. Now, F1 is 5 newtons, 20 degree with respect to x-axis, and it's in the 4th quadrant. Theta is with respect to x-axis, so I can write it like this. I can write 5 cosine of 20, and then 5 sine of 20. Then, because the F1 is in the 4th quadrant, this is positive, this is negative. Okay. Now, I could have done this. I could have said it's 5 cosine of 340 and 5 sine of 340 without putting any, manually any signs, right? This would have been also correct. 5 cosine, because, I'm using then this theta instead. Okay, that would have been correct. But if I'm using this 20, right, for example, then I need to manually put the negative for the y component. For the x1 becomes 8 cosine of 60 and 8 sine of 60 is in the 1st quadrant, so both of them are positive. Okay. That means this will be your first, 2nd step, right? Table. First step is the free body diagram. 2nd step is the table. And then those are your equation. 1 is equation 2. That means, for example, I go here, I can say, okay, 3rd step, getting those equations. Equation 1 gives me net force in the x direction, which is equals to then F1x plus F2x, right? So technically it's like this. So then what I get here is, let me see, yeah, both of them, so F1x plus F2x, because both positive. So end up being 5 cosine 20 plus 8 cosine 60, right? So I basically add the x components. And I'm gonna get 8.7 newtons. Equation 2, then I calculate the y components. In a y direction, we have then 5, negative 5 cosine of, sorry, sine of 20 plus 8 sine of 60. And if I add those, I'm going to get 8.7, sorry, 5.2 newtons. Okay. Those are the components. Those are the X and Y components of my net force. Now, what I'm going to do next is this. Remember, I want to find acceleration. Okay, I want to find acceleration in terms of its magnitude and direction. And there are two things I can do right now. Let me show you, like, let's say, first way. First way, I can then do this. I can find X component of acceleration, which is basically net force in the X direction over mass. That means I take 8.7 newtons divided by the mass of the object, which is 0.3 kilogram, and find the acceleration in the X direction, which is 29 meter per second square. Same way, I find the Y acceleration, which is net force in the Y direction over mass, 5.2 newtons over 0.3 kilogram, and I get 17 meter per second square. And now that I have components of the acceleration, I can say that acceleration magnitude is 29 square plus 17 square, and find the magnitude of the acceleration vector, which is then 34 meter per second square. Or then I can say then, also then direction, which would have been inverse tangent of 17 over 29. This would have given me 31 degrees. All right, so magnitude, direction. That's the first way of doing that. The other one will have been like this. First, I find the net force from the components of the net force, which would have been square root of 8.7 square plus 5.2 square. So that means, calculating this. Let me see. So 8.7 square plus 5.2 square root of that. So I get 10.1 newtons. Then I find the direction, which would have been inverse tangent of, a 5.2 over 8.7. So let's see what I get. Well, not surprising, I'm getting 31 degrees. Why? Because the direction of the acceleration as a vector proportional to the direction of the net force as a vector. If this is 31, this has to be 31 as well. But then how do I get the magnitude from here? Well, acceleration then is equals to the net force over mass. That means I can also use the magnitude of the net force, which is 10.1, divided by 0.3 to get the magnitude. So if I do 10.1 divided by 0.3, I'm getting 34 meter per second square. Exactly same with the previous method. That means both of those methods can work. That means first find the X and Y component of the acceleration, then use those to find the magnitude and direction of the acceleration, or find the net force and the net force's direction, which means that net force has the same direction as acceleration, then do net force divided by the mass to get the magnitude of the acceleration vector itself. All right, so both methods will work. All right, so this concludes chapter 4.